and say other tissue cells, I mean, we never think of momentum as an issue, or inertia for that matter. I mean, I understand the model does well to describe the transition and so forth, but I mean, are we supposed to think of that as an effective interaction and not really collisions? I mean, it seems because you speed the movies up, right? Keratocytes are fast, but they're not that fast.
Yeah.
So, what would you say about modeling tissues and things like this?
Yeah, you have to, yes, the momentum or the mass, inertia does not play a role. But then if you are a careful physicist, you have to see where it is and how it is lost and why it doesn't have to be taken into account, and how you can use the Newton's equations of motion without acceleration.
Right.
But it can be done, and it would be too long for me to tell you, but we wrote this down, it's in a paper, and I'm happy to show it to you. But it's a calculation.
Charlie Risky on evolution of collective behavior in animal groups.
Does it work?
Yeah.
Thank you very much. Finally, this work. Almost for last 2 times, every time I come here on the to present, something happens to this laptop. Anyway, thanks again. So I'm going to talk about evolution of collective migration. This work has been done in Ian Cousin's lab at Princeton University. Colin, he was a visiting graduate student from University of College Dublin. So we have had a very good introduction to collective systems. I don't have to really repeat any of this. We have seen some of these pictures. These patterns occur due to repeated local interactions among individuals who constitute these large-scale systems. And these behaviors are a result of millions of years of fine-tuning by evolutionary forces in terms of natural selection, adaptation, and mutations. So one can ask questions: why did natural selection, why did nature choose collective behavior? If you think from an engineer's perspective, one would usually want to optimize a collection, a group of robots, for example, to have an optimal behavior. On the other hand, evolution doesn't have any such designs. It's interested only in that single individual, and whoever does the best gets chosen as who passes on his genes to the next generations. So under those conditions, the question of interest would be, how is that the natural selection, which acts at the level of an individual, leads to some of these local rules, which in turn leads to these large, very cooperatively appearing patterns and at much higher levels of organizations. So with this broad question in mind, we will look at the system of collective migration. Migration at axis can happen because there are individuals who are trying to climb up certain gradients. These gradients can be resource gradients. We have seen an example yesterday in a talk, and then we have also seen animal migration examples in Ian's talk. And those individuals who can perform those kind of gradient detection and climb those gradients, we can call them informed. I'm calling them informed just using Ian's terminology of informed individuals or leaders, and there are other set of individuals who do not know what to do. They are uninformed or they are naive. So this paper in Nature showed that if you have a large group, all you need is a very small subset of your whole system who need to know how to measure these gradients, or who need to have the right information. If the rest just stick with the crowd, the whole group tends to have high accuracy. Now, we can try to think of this question in an evolutionary context. If we have this large group with blue guys representing those who can do certain gradient detection mechanism, and the green ones who are naive, who just follows the nearby individuals, the group as a whole reaches the right target. Probably it's a foraging patch or a mating ground, and in the end, everybody in the group gets nearly equal benefits. On the other hand, those guys who did this task of gradient climbing, they have probably invested some sort of energy for having that cognitive machinery, or they're risking their lives by not being able to pay attention to the predators who might attack them, and so on. So if we assume that there is a cost involved in such a task of gradient climbing, gradient detection and climbing, those guys who are following are actually paying a lesser cost but getting the same, nearly same benefits. So the question that one can ask is, what would evolution lead to? Is are these green guys like these cancerous cells we saw yesterday who take over the whole populations, and in the end you're left with no guy who could do the gradient climbing, and you're left with basically individuals who are just sticking around? Or how would natural selection balance the task of doing a migration versus these guys who can cheat and grow the cancerous cells? So with that motivation, I'll introduce a very simple model based on Nature paper by Ian, where individuals have certain phenotypes that they can evolve. So the phenotypes can be one of sociality. The sociality comes from the fact that individuals don't want to go too close to each other. They repel if they are very close. On the other hand, they have this zone of orientation and attraction where they try to go towards other individuals, and they try to align themselves with other individuals within that local region. On the other hand, there can be certain individuals who have these capabilities. In fact, everyone can have this. We don't know what proportion of the population is going to have this. We will let the evolution choose what it wants to choose. So individuals can also have this phenotype, which is a gradient detection ability or degree of informedness. This parameter omega g here determines how accurately one determines the gradient. If I choose the x-axis to be the right gradient to climb, higher the value of omega g, more accurately does one measure the gradient. And we can describe this theta, which is a deviation from the right direction, through some simple Einstein-Oriented kind of process. One can also introduce spatially temporally correlated noise. We have done both kind of scenarios in the system. And then once you have determined your social direction and you have determined the desired direction that you would want to go, you weight them in a vectorial fashion using this sociality vector. So just remember that we have two phenotypes. One is sociality, which determines to what extent you would want to weigh your sociality versus the gradient climbing capability. And the detection ability enables you to determine where you are going in a very accurate fashion. Higher the ability, more accurately you climb the gradient. So where would evolution lead to in this parameter space? And that crucially depends on what exactly are the benefits and costs involved in doing these actions. So as these individuals move around, I assume that if they're climbing in the right direction, they get a benefit which is proportional to the distance they travel in the right direction. So if you have an individual with certain ability to climb the gradients, if the guy makes a random motion, the projection of that vector, position vector from the beginning to the end on the x-axis, which is the right direction, provides the benefit. And this benefit increases in this nonlinear fashion as the gradient detection ability increases. On the other hand, having this ability also incurs some cost. We make an assumption that this cost increases linearly as a function of the ability. If you put both of these together, an individual, just one individual, there are no other individuals around now. The individual will have an optimal gradient detection ability. If you don't want to invest too much that the benefit you're going to gain is lost by just the cost, there is certain optimal detection ability that one would like to invest if you are alone. However, when there are other individuals around, there is no guarantee that this strategy will work in an evolutionary sense. So the question is, how do we determine that? So we use a simple following selection algorithm. We start with the large number of individuals in this continuous space who perform motion in discrete steps, and an individual has certain phenotype value which is randomly chosen in a parameter space of these two parameters, detection ability and the sociality. And then they move according to the rules, equations of motion for over one generation, which is substantially long, that each phenotype obtains certain equilibrium value of the fitness. Then we calculate the fitness for each individual, which is just the benefits minus the cost involved in doing, depending on how much exactly they did the gradient climbing versus how much cost they incurred, depending on the interaction value they had, phenotype value they had. And then using a simple roulette wheel selection, you choose though you reproduce every individual proportional to the individual's fitness value. And repeat this process until an equilibrium in the phenotype distribution is obtained. These simulations are performed on GPUs. GPUs are new technology developed by, which is very well marketed by NVIDIA these days, where you can simulate large number of particles. This, for example, simulation has 16,000 individuals. This is a real-time simulation which I just did on my laptop, and so it's pretty fast. You can do very fast simulation. Nevertheless, evolutionary calculations are even with this kind of scale, it takes very, very long time to equilibrate. So here is a result of one of the evolutionary simulations where you're investing certain cost in having a goal. So what you find is that if you start with a somewhat uniform distribution of detection abilities and sociality in terms of the whole population, the population spontaneously emerges into a bimodal population. One population having which is relatively high gradient detection ability but low sociality. Those guys don't want to be with others, they just want to keep climbing the gradient. On the other hand, there are guys who have basically almost nearly zero value of detection ability, but they are just sticking around with others. They have high sociality, they want to follow others who are trying to climb the gradient. So this population spontaneously emerges into a mixture strategy who coexist, and in fact, if you start with one population, it spontaneously breaks into the other, which I will show you in the next simulation. And of course, this evolved strategy, one might ask, what exactly is this evolved strategy doing? If I assign these phenotype values to a large number of individuals, and if I assign random positions and velocities to these guys, they spontaneously form into groups containing guys with high detection ability and guys who are just social, and they move in the right direction. Of course, one can imagine extreme scenarios where there is no cost involved at all in having a machinery. Then naturally, you would expect that everyone would want to have the best detection ability by themselves. There is no really point in cheating. On the other hand, if the cost is very, very high, those guys who cheat completely take over the population, and there is absolutely no migration taking place at all. So it's in these intermediate regimes that you find bimodal strategy. Here you see a simulation where you start from a single population, and the population spontaneously splits into those who can do detection and those who just follow. Yeah?
How reachable is it to assume that gradient detection and sociality can be transferred to the offspring?
So every individual, when you reproduce for the next generation,
They retain the gradient detection.
yeah, they retain the exact phenotype value the parent has, but there is a small mutation on top of that. That essentially kind of gives a drift in the right direction. But the offspring have nearly same phenotype values the parent has. But the number of offspring produced by a parent depends on that parent's fitness value. Smaller the fitness, lower likely you are to produce in the next generation. That way, all the guys who are not doing well get killed out in the process. This is an evolutionary branching process. The y-axis is time, generations, and the trajectory shows how the population split into two branches. Of course, the timing gets really hard when there are spatio-temporally varying gradients, because you can easily get stuck on these local optima, and you can easily miss the global gradient which is present on top of that. In those situations, what you find is something very counterintuitive, which is that you need to have, it is the naive individuals, the guys who don't know what exactly the guys who just follow others, they are the ones who have certain inertia, and they kick the guys who can detect and who are stuck on the local optima, and they take out those guys out of the optima. And so in a way, if you have everyone who can do detection, that's not a good strategy at all. In fact, the strategy, mixed population strategy, where only few people can detect and the others are just following, and those are the guys who can take you out of the local optima. And I can also show you one movie where it's not showing up for this, I don't know. Okay, anyway, I'll speak it. So yeah, those are the main reasons. So the evolution which is acting on selfish individuals, not on groups, however, interestingly enough, produce properties which are as if the group as a whole is trying to optimize itself. In this specific problem, the strategy is, the evolutionary same strategy is, we have a mixed strategy where there are certain number of guys who can do a gradient detection, whereas the others who just stick around and follow the rest of the population. And this is a very interesting thing because the strategy that one guy chooses depends on what the rest of the population is doing. There is a frequency dependence. And this whole evolved population performs collective migration. So we are working more on this problem where only when you have only local information how exactly evolutionary dynamics takes place, what are the effects of density, mutation rates, and other issues such as cost structures, and we are trying to model, make abstract model applicable to more specific systems like social bacteria and things like that. With that, I would like to thank everyone in our lab with lots of discussion, and thank you very much for listening.
If Fernando's here, can you do your laptop? Any questions?
What if the unfit reproduce more than the fit?
What if unfit to produce more than?
Yeah.
In the algorithm,
Yeah.
probably the unfit population will take over. But there is no biological reason to have an algorithm like that.
Well, humans.
Well, fitness here is defined as a reproductive probability. So.
I was just wondering, like, if that's.
Usually, yeah.
Yeah.
And obviously they will take over. I mean, whoever reproduces more takes over. But usually, the way selection algorithms work is those guys with higher fitness values are more likely to reproduce in the next generation. That's the definition of fitness, actually. That's how fitness is defined.
So your definition of evolution is that, or the fitness is that whoever can find the food or go in the right direction.
Exactly.
So isn't that very far away from the reality? Or
Well, not necessarily. I mean, I don't know.